Have you ever wondered why a website hosted in London feels just as fast in New York as it does in Tokyo? It shouldn't be possible. The speed of light is roughly 300,000 kilometers per second, but in fiber optic cables, it's actually about 30% slower. For a signal to travel from London to Sydney and back, the physics of our universe dictates a minimum round-trip time of about 160 milliseconds. Add in routing, switching, and processing, and the internet should feel, well, sluggish. This is the latency wall. But today, we don't hit that wall. We bypass it. We defy the physics of distance using a global network of distributed servers known as a Content Delivery Network, or CDN. In this video, we're going deep into the internals of how these systems actually work, from Anycast routing to edge computing. To understand CDNs, we first need to look at the origin server. This is where your actual application lives. When a user in Singapore requests a 5 megabyte image from an origin in Virginia, that data must traverse dozens of routers across the ocean floor. A CDN changes the topology. Instead of one central server, we deploy hundreds of edge nodes or points of presence known as POPs. These are many data centers located at the intersections of major internet service providers. The CDN's job is to pull content from the origin once and then serve it to thousands of local users from the edge. By moving the data closer to the user, we reduce the last mile distance. It's the difference between driving across the country for groceries versus walking to the corner store.
But how does your computer know which edge node to talk to? This is where the magic of Anycast routing comes in. In a typical network, every IP address is unique to one location. But with Anycast, multiple servers across the globe all advertise the exact same IP address to the internet via BGP, the Border Gateway Protocol. When your request enters the internet, routers look at their routing tables and send your packets to the closest advertised destination based on network hops. It's like having a dozen pizza shops all using the same phone number. The telephone exchange simply connects you to the one with the shortest wire. This happens at the network layer, meaning that it's incredibly fast and happens before a single byte of your request is even processed.
Once you've reached the edge node, the next challenge is caching logic. A CDN isn't just a mirror, it's an intelligent cache. When a request arrives, the edge node checks its local storage. If the file is there, that's a cache hit, instant delivery. If not, it's a cache miss. The node then fetches the file from the origin, stores a copy, and serves it. But how long should it keep that copy? This is governed by the time to live, or TTL. Setting a TTL is a balancing act. Too long and your users see stale content. Too short and you overwhelm your origin server. CDNs use complex eviction algorithms, like least recently used, to ensure that the most popular 20% of your content, which usually gets 80% of the traffic, stays in the fast lane.
But what about dynamic content that can't be cached, like a user's shopping cart? CDNs still provide a massive speed boost here through dynamic acceleration. To establish a secure connection, your browser and the server perform a TLS handshake. This requires multiple round trips. By terminating the TLS connection at the edge node, which is physically closer to you, the handshake finishes in milliseconds instead of hundreds. Furthermore, the CDN maintains warm, persistent TCP connections from its edge nodes back to your origin. This bypasses the TCP slow start phase, allowing the data to flow at maximum speed immediately. Even if the data itself isn't cached, the pipe it travels through is preheated and optimized, cutting down the time to first byte significantly. To manage millions of requests without crushing the origin, modern CDNs use a hierarchical architecture. Think of it as a pyramid. At the bottom are thousands of small edge POPs in every city. Above them sit a few dozen regional shields. If an edge POP has a cache miss, it doesn't go to the origin immediately. It first asks the regional shield. This request collapsing ensures that if 100 different edge nodes all need the same new file, only one request actually goes back to your server. This protection is vital for surviving the hug of death when a piece of content goes viral and traffic spikes by 10,000% in seconds. The CDN acts as a massive shock absorber for your infrastructure.
Cache invalidation is famously one of the two hardest problems in computer science. When you update a product image on your site, you need every edge node in the world to delete the old version instantly. Modern CDNs use a global control plane to propagate purge commands. In the past, this could take minutes. Today, it takes milliseconds. CDNs use a variety of techniques, such as surrogate keys or tag-based purging, which allow you to group related objects. For example, you can tell the CDN to purge everything tagged with /product/123. The control plane sends a tiny message to every node, which marks those specific bytes as invalid. The next time a user asks for them, the node knows it must fetch the fresh version, ensuring the global state is synchronized almost instantly.
CDNs are also the internet's primary shield against distributed denial of service attacks. Because a CDN has a massive aggregate bandwidth, often measured in hundreds of terabits per second, it can absorb volumetric attacks that would instantly melt a single server. At the edge, CDNs perform scrubbing. They look for malicious patterns in the traffic, like a single IP sending 10,000 requests per second, and block them before they ever reach your origin. They also provide a web application firewall, or WAF, to block SQL injection and cross-site scripting attacks. By the time a request reaches your actual application, it has been vetted and cleaned by a global army of security proxies.
The future of CDNs is edge computing. We are moving beyond just storing static files. Today, you can deploy actual code, like JavaScript or WebAssembly, directly to the edge nodes. Platforms like Cloudflare Workers or Fastly Compute allow you to run logic closer to the user. This means you can personalize content, A/B test UI, or even query a distributed database without ever sending a request back to your central origin. We are effectively turning the entire internet into one giant distributed computer. The distinction between the server and the network is disappearing. By distributing the compute power, we minimize the latency of decision-making, taking us one step closer to a truly instantaneous web experience. CDNs are the unsung heroes of the modern digital age. They are the reason 4K video streams don't buffer, and why global commerce can happen in real time. By intelligently caching data, optimizing routing through Anycast, and moving compute power to the edge, we have built a system that effectively hides the limitations of physics from the end user. The next time you load a page instantly, remember, there's a global network of thousands of servers working in perfect harmony just to save you a few hundred milliseconds. Thanks for watching. If you enjoyed this deep dive into internet internals, consider subscribing for more technical explainers. I'll see you in the next one.